Hi everyone, my name is Andres. I'm one of the authors of this paper, Guiding Symbolic Natural Language Grammar Induction via Transformer-Based Sequence Probabilities. And what I'm going to present is basically a methodology that we're proposing for grammar induction using a neuro-symbolic approach, the combination of neural techniques with symbolic techniques. This is, as I mentioned, mostly a methodology. The tests and building the whole pipeline for doing it is still under construction. But yeah, the idea is what we're presenting today. So what's unsupervised grammar induction? It's about learning how a language is structured, learning the grammar rules of a language without the use of explicit parsers, for example, without using any hints on how the structure of the language is, annotations about the structure of the language, just using plain text to discover it or to induce it automatically. So this has been a problem that has been around for a long time, for decades, has been tackled. Still, even with such a long tradition, the results are not great yet, and they're definitely, especially unsupervised grammar induction, still considerably worse than hand-coded grammars or even supervised learning of grammars, which of course work fine for languages that have a lot of annotated data, but doesn't work for others. So this is just an example of what we can do with these kind of grammars. We can create parse trees, which tells the structure of a sentence or the structure of any sequence of words in a language. This is using a hand-coded grammar, which is called a Ling grammar in English. Okay, with with neural networks, especially with transformers, we have seen a big improvement in the quality of the language models that are created, that are learned unsupervisedly by these models. This is just a very popular example of what GPT-2 can do. Generate sentences that are very realistic, at least grammatically realistic. This one is talking about unicorns, right? But it's a sentence that has a very good grammar, very good English grammar. And so by seeing these kind of examples that these networks can make, we can see that they have internalized the grammar. Just by reading a lot of text, they somehow, in the weights, in the billions of weights that they use, they have internalized the grammar. So people have been trying to extract that grammar to use it for their purposes. Now, in this case, maybe parsing trees, creating parse trees from sentences. So this is an example of a paper from last year, where they noticed that by exploring many of the layers in the transformer, they find some heads that do show some specific attention to some special components of the sentence. In this case, this head that they're talking about, or this it's paying attention to noun modifiers. So the words that modify a noun pay attention to the noun. So we see here that and complicated pay attention to language. In the huge new pay attention to law, etc. So it works fine for this example, from these examples, and there are some other heads that pay attention to other parts of speech or to other syntax in the sentences, but it's very it's hard to find these good examples. They're kind of cherry-picked. Each training of a neural network will have different layers that learn different things, so it will be hard to actually come up with a grammar from there. And it also doesn't explicitly say how the grammar is working. It's just like some layers are paying attention, so it's not an explicit grammar that we're learning from that. It's useful for the language model because it can produce good grammar, but not for our purposes of inducing a grammar. So what we're proposing is, instead of looking inside the weights and the layers of the neural network, we propose to use the transformer, the good capabilities for a language model that it has, to use it as an oracle, in this case, like a sequence probability oracle or sentence probability oracle. What does that mean? Okay, we're gonna ask a transformer how good a given sentence is according to the language model that it has, according to to what it learned from some language. How are we gonna use this? Okay, here we have a very high level schematic of how this could work. If you have a way of learning some grammar rules from a text corpus, which, by the way, I have worked with other people in an unsupervised grammar learning pipeline, which without supervision can symbolically create grammar rules. These grammar rules are not perfect, and the pipeline can be improved, but what we're proposing here is to use or to clean those rules that the grammar learner is creating using the transformer. This is just a way in which you could create the grammar rules, unsupervised language learning, but you could use any other way in which you produce language grammar rules and then clean them using this oracle that we're talking about. What is the oracle doing? So from the grammar that is inferred somehow, you produce sentences. Using a sentence generator, you take a rule and then produce sentences. And then using the transformer, using the language model, using these deep neural networks, we can evaluate how good the sentences are that were created with such a rule, and thus decide if that rule is worth including in our grammar or not. So we iteratively clean the grammar, and we can also find ways of creating other new grammars and then testing them in similar ways. There could be also a loop with this grammar learner to change the rules or to add new rules, for example. No? So how are we, the crucial question here is, how is this grammar rule evaluator working from the oracle or from the transformer? We propose this. We propose that with a given rule from the grammar, in this case we have a very simplistic linked grammar type rule in which the word kids can be connected to the word small and to the word da. This negative sign means that it can be connected on the left of this word. So kids connects to small on the left and to da on the left. So it can create sentences like this one, the small kids, because both small and kids are connected to the left of kids. And then we can modify this rule, like let's say try to break the rule or create the opposite rule. For example, small plus and da plus, which means that these words connect to the right of kids. So it will create sentences like this one. Kids, small da, play football. The order of the words is also encoded in this rule. So then we can ask once we generate sentences from the rule that we're testing and the opposite rule or some way of breaking the rule, we can ask the oracle, what's your, how good of a score does this sentence get in your language model, and how good of a score this other sentence gets in your language model. Then if the two scores are similar, that means that this rule doesn't really create significantly better sentences than the other one. So that means that this rule might not be very good. But if the quality of this sentence is way better than this one, which, for example, in this specific case, it would be, this sentence would have a high score assigned by BERT, for example, which is what we're using in this project, compared to this other sentence, right? Like this sentence, we can distinguish it as being better English. So then we can say that this rule is worth including in our grammar because it creates way better sentences than the opposite rule. So now a crucial question is, how is the transformer going to score these two sentences, right, to be able to compare them? So for that, we propose the sentence probability estimation, which is basically what's the probability of a sentence, by taking the joint probability of all the words that belong to that sentence in that specific order. We separate this probability into two components, a forward component and a backwards component. That's because we're, in this particular implementation of it, we're using BERT, and BERT has bidirectionality, so we want to take advantage of both. So we just do an average, a geometric average of both of the forward and backwards. By the way, this technique or this methodology that we're proposing can be used with any transformer. Even like if new transformers come out that have better language models and better internalized grammar, then we can just substitute it for the one that we use now, which is BERT, and have the methodology doesn't care about who is the oracle. Basically, it's just as long as you can get an estimate of the probability of the sentence, then you can use that. Okay, so how do we get these forward and backward probabilities? We simply decompose the joint probability into conditional probabilities in the normal way. This is the forward one. The backwards one would be very similar, just we start with Wn here. What's the probability of Wn times the probability of Wn minus 1 given Wn, etc. Right? And each of these conditional probabilities, each of the terms, can be obtained from BERT by asking BERT what's the probability of word Wi given all of these words. So all of these words are unmasked, and you mask Wi and all the words that haven't been given to the sentence which are not included in this term, and then you obtain the probability of that specific term, and you do that for every term to obtain the forward probability. A graphical example might be helpful. So we have here the sentence "she answered quickly," which we tokenize into 3 words, and then these are the probabilities that we need to calculate the forward probability of the sentence. The probability of she times the probability of answer given she, etc. So then we mask all the words, and we ask what's the probability of she. It's the probability that the mask number 1 is equal to the word she. What's the transformer estimation of what is the probability that this mask will come up as she without any more information, so all the other words masked. And then for the conditional probability where she is given, then we unmask she, and then we say what's the probability that mask 2 is answered, right, which is what we want, without information for the other masks, etc. We do the same for every other word, and that's how we obtain the forward probability. Similar thing for the backwards probability, and that's how we estimate the probability of a sentence using the transformer, in this case BERT. So now we also realize that this idea of using the oracle to tell us the probability of sentences can be very useful for other parts of a pipeline. Expanding the input that we give to the symbolic grammar learner, to the unsupervised grammar learner, we need to have words divided into categories. So words that are annotated with parts of speech. We do this unsupervisedly as well by clustering words, like by creating word embeddings that for each of the instances or each of the words in the vocabulary, and then we cluster them and get parts of speech. So with this tagged corpus we can create grammar rules. That's how our pipeline normally works, and we can use the transformer here also to create the word categories and to create the word embedding, the word senses. How do we do that? Well, word embeddings are very commonly used for both of these tasks: word sense disambiguation and word category formation. These are examples from modern times. Well, kind of this one. But yeah, in here they do word embeddings, and they realize that this is using I don't remember, probably Word2Vec or some other neural network, in which the words that fall closely in this n-dimensional space are related in semantics or in syntactics. Like verbs sometimes fall together, words talking about a city, for example, here fall together. And similarly for word senses, this is a paper called "Does BERT Make Any Sense?" and they use only the instances of the word that they are interested in. So for example, bank. These are all instances of the word bank in their corpus, and then they cluster them and realize that all words in pink here use the word bank as a financial institution, all the words green here use it as a sloping land, etc. So it's possible to use these word embeddings. People have been doing that for a while. We proposed that instead of using the hidden layer of some network, some neural network, or something that we don't have a very clear understanding of why it ends up being like that. I mean, it's of course based in the distributional hypothesis, but we want to have a little bit more control. So that can be done by building embeddings that we know what they contain. So we propose to use embeddings obtained from a matrix that we create by using in the columns all the vocabulary of the corpus, and as rows every sentence in the corpus, where one at a time we are removing one of the words and leaving it as a blank. Why are we leaving a blank here? Because then she is the same sentence that we used in the example before. She answered quickly. So instead of using answered here, we would fill this sentence with every other word in the vocabulary, or every word in the vocabulary. So here we have she quickly, she saw quickly, etc. For every word, we have an entry in the matrix combined with a sentence, right, with a blank, and then we estimate the probability of that, of each of these sentences, using the oracle again, like the transformer. So this way we can create embeddings that will embeddings that have similar meaning in the rows. So here, if we take the rows, we can use instance of the words to see if these instances have a similar behavior depending according to the words that you're filling in. If you use columns, then you are checking if the word in the vocabulary has a similar use to other words in the vocabulary, because it will have a similar probability in the first component if these two words have a similar function in the language, right? If she has a similar function to saw, then she answer quickly would be similar to saw answer quickly, which in this case is not. So we can tell that she and saw will have a very different embedding, because each of these components of the embedding would be very different for these two. But for words that have a similar function, for example, he would have very similar probabilities as the word she here in every fill in the blank sentence. So then we can cluster them and obtain word categories. For word sentences, as I mentioned before, word sentences, sorry, you would use the place where, or the word that appeared in this blank originally. So in this case, she. This would be the embedding for the word she. And we're saying which other words fill the same function as this instance. So because she is not a very good example. Let's say saw. Saw can have different meanings, right? Can function as a verb or can function as a noun. So then this instance is taking one of those meanings. Let's, in this case, well, this saw is functioning as a verb. So then this instance would be similar to other verb uses of saw, but very dissimilar to noun uses of saw. So then we can distinguish them, cluster them, and obtain word senses. So thank you for your attention, and I hope if you have any questions, you can let me know in the discussion.